What will be the change? It started with 62 and at 6, so final minus initial, divide by time interval, which was 35 minus 0. Then the final answer is 1.62 into 10 power minus 1.6 into 10 power meter per second square. That is the deceleration of this aeroplane. The force, the resultant force, we have the mass and we need the resultant force. So F is equals to ma. For resultant force is mass multiplied by acceleration. The mass of the plane, that's given 2.5 into 10 power 5, and the acceleration or deceleration is 1.6. So 2.5 into 10 power 5 multiplied by 1.6. The final answer is 4 exponent 5 Newton. So that is the resultant force experienced by this aeroplane to reduce the speed from 62 meter per second to 6 meter per second. Momentum of aeroplane when its speed is 6 meter per second. Momentum is the product of mass and velocity. So how we'll find the momentum? The mass of the plane, that is 2.5 exponent 5, and the speed at which it is moving, that's 6. So you multiply the mass with speed or speed with mass, you will get the momentum. What is the momentum of this plane? That is 1.5 exponent 6. And the unit of the momentum, it can be kilogram meter per second, or you can also use Newton second. Unit of impulse, unit of momentum or change of momentum, all are same. So just kilogram meter per second. The next question, at t is equals to 35, the airplane stops decelerating and moves along the runway at a constant speed. On the figure figure 1.1, sketch a shape of a graph for a distance traveled by the airplane along the runway from t is equals to 0 to 50 seconds. You are not required to calculate the distance. Look, first what happened? For first 35 seconds, it is decelerating, and we know distance time graph, the slope represents speed. So if something is decelerating, it means the speed should decrease. So if speed is decreasing, means the slope should decrease. So first part of a graph for 35 seconds, we should represent that the slope is decreasing. And then from 35 seconds onwards, it moves with a constant speed. Constant means speed means slope should be constant. And how we represent a constant speed? So it should be a straight line from 35 to 50. So this part, the slope is decreasing. It means the speed is decreasing. And the other part, the slope is constant. It means the speed is constant as well. Next question, as the airplane decelerates, its kinetic energy decreases. Suggest what happened to this kinetic energy? So what happened to kinetic energy? Its kinetic energy transformed into heat energy. So wasted in the form of heat because of the friction between the tires, ground, and the brake, thermal energy. Next question. Figure 2.1 is the extension load graph for a light spring S. Extension is on y-axis and load is on x-axis. State the range of a load for which it obeys the Hooke's law. For which range of a load it is obeying the Hooke's law means the line is straight. So from 0 Newton to 8 Newton, it is obeying the Hooke's law. Use information from figure 2.1, determine the spring constant K. The spring constant K is always we find for a linear part, K is equals to force divided by extension. Or you can also, in this case, when load is on x-axis and extension on y-axis, the slope is reciprocal to K, or K is reciprocal of slope. Either you can find the slope and take the reciprocal, or F divided by E. So as we know, F is equals to Kx. So use the graph, the value of the force, if you took 8, then the extension will be, I think it's 15 centimeters, so it will be 8 divided by 15, and the final answer will be Newton per centimeter. So K is equals to F divided by E, or F divided by X. So this was 8, 15, so that will come out 0.53 Newton per centimeter. A second spring identical to spring S is attached to a spring. Two springs are attached to a rod as shown in figure 2.2. A load of 4 Newton is suspended from the bottom of the spring. The arrangement is in equilibrium. State the name of form of energy which stored in the two springs. So which form of energy is stored? Because when object deforms, changes its shape, size or length, so it stores elastic strain energy or elastic potential energy. You can mention elastic potential or elastic strain. Then determine the extension. How you will determine the extension? Because what happened, this 4 Newton load is for first spring and for second spring. So both springs, as we know, force and extension are directly proportional to each other. So both springs will experience the force of 4 Newton, and 4 Newton, how much extension it will cause for one spring? So according to the first part, we have to determine the extension for this whole arrangement. And you can see the 4 Newton force, how much extension it is causing. It is causing approximately 7.5 is there for one spring, because two springs are there connected end to end, and a weight of, or a load of 4 Newton. So this experience a downward force of 4 Newton, this will also experience 4. So 4 Newton cause an extension, the increase in length of 7.5 for each spring. So if each spring extended by 7.5, then the total extension will be twice or double. So it will come out to be 15 centimeter. Look, if the arrangement was like this, like two springs connected in this manner, and you attach a load of 4 Newton. So in that case, each spring will experience 2 Newton force. But whenever you have spring end to end are connected, the total force is equals to the force experienced by each spring. Like example, if I attach a 4 Newton force load, so spring 1, how much force it will experience? 4 Newton. For spring 2, how much force it will experience? Also 4 Newton. So this spring experience a force of 4 Newton, and the other spring, and the two springs are identical, that will also experience a force of 4 Newton. And from the graph we know 4 Newton cause an extension of 7.5. So there is extension of 7.5 for both springs, each spring. So the total extension will be how much? 7.5 plus 7.5. So it will be 15. So this will be 15 centimeter. Then the load is carefully increased to 6 Newton. Calculate the distance moved by load to new equilibrium position as the load is increased from 4 Newton to 6 Newton. So as it is increased from 4 Newton to 6 Newton, look, when the force is 6 Newton, how much is the extension? For each spring, the extension will be 11 for each. So, and the total extension for the combination, like when there is a 4 Newton, the total extension for the combination was 15. When we attach a 6 Newton load, the total extension for the combination, because each spring is 11, so the total extension will be 22 centimeter, because 11 for each spring and two springs are there, each experience 6 Newton, so total will be 22. How much it moves when the load is changed from 4 Newton to 6 Newton? So 22 minus 15, which is equal to approximately exact number, because this number is there. So 22 and 15. So according to this graph, when we use our graph, it will come out 7 centimeter. You can use the formula and you can also find the answer for this, because a load is carefully increased to 6 Newton, and calculate the distance moved by the load to new equilibrium position as the load increases from 4 Newton to 6 Newton. Or you can also work out like how much increase is there, a 2 Newton force, because the increase in 2 Newton force, how much extension for each spring? That is approximately, like, it look like 3.75. So if I took this value 3.75 centimeter, then for 2 it will be 3.75 multiplied by 2, which is equals to 7.5. So depends on how we are solving, because the exact number, even when we took this 6, it was not exactly 11, it was a bit more than 11. That is why in marking scheme you will find they write 7.5, because they took that when we increase the force of 2 Newton, how much is the increase in the length or extension, as the spring is obeying a Hooke's law. Is it clear, this question? Figure 3.1 shows a gas trapped in a sealed end of a tube by a dense liquid. So there's a dense liquid and a gas is trapped. So idea is that as the gas is trapped, the pressure exerted by the trapped gas balanced with the pressure of the atmosphere. That's why the two levels are same. So we can say pressure of the gas is same as pressure of the atmosphere. The scale marked on a seal end of a tube is calibrated to read the volume of a trapped gas above the liquid. Figure 3.1 shows the initial volume V1 of a gas, which is 60 cm3. The pressure of the atmosphere is 1.5 exponent 5. State how figure 3.1 shows that the pressure of a trapped gas is equal to the atmospheric pressure. So how this figure shows that atmospheric pressure and the pressure of the gas are equal. So both of the liquid levels are same height, or both ends of liquid level in the two limbs are same in height. Explain in terms of momentum of its molecule why the trapped gas exert a pressure. So why there is a pressure from the gas molecule in terms of momentum. So because it's a gas, so molecules are moving randomly. They're continuously changing the momentum, and change in momentum cause a force which act on unit area to create pressure. So gas molecules moving randomly. So they're continuously colliding. And you have to use the term momentum because they specifically mention in terms of momentum. So there should be a term momentum in the answer when you write, like as they're changing a direction, they changes the momentum, and change in momentum cause a force which creates pressure on a unit area, or which there's a force on unit area which create a pressure. The next part, more of the dense liquid is poured into the open end of a tube. The level of the liquid in the both sealed and the open end of a tube rises. The temperature of a trapped gas and atmospheric pressure remain same. So in a sealed end of a tube, the volume V2 is 50. In the open end, the liquid surface is 15 centimeter above the new level. Calculate P2. So how we'll calculate P2? We'll use the formula for Boyle's law, that P1 V1 equal P2 V2. And what are the values? The original pressure was same as the atmospheric pressure. Original volume was given. The P1 was the initial pressure, atmospheric pressure. V1 was the original volume which was given. So that will come out 1.2 into 10 power 5. So the initial pressure is due to atmospheric pressure, initial volume, final pressure we are finding, and final volume is given in the question. The next part, calculate the density of the liquid. So how we'll calculate the density of the liquid? To calculate the density of the liquid, we should know pressure is equals to density, gravity, and depth, or rho gh. But first what we need the pressure of the liquid, because to use this formula we know pressure is equals to density, pressure exerted by liquid, density, gravity and depth. In terms of this equation, as you can see, there is an atmospheric pressure, there is a pressure from the liquid, and there is a pressure from the gas. So pressure from the gas, which is P2, pressure of atmosphere and pressure of liquid. So when we write the equation, we can say pressure of a gas is equals to pressure of liquid plus pressure of atmosphere. So first the pressure of the gas minus the pressure of atmosphere will give us the pressure due to liquid. First we should get the pressure due to liquid by taking a difference, the gas pressure. And what is the gas pressure? That is the second value of pressure, minus the atmospheric, will get the liquid pressure. And using a liquid pressure, so 1.5 1.2 exponent 5 minus 1.5 exponent 5, that will give us the liquid pressure. And after getting the liquid pressure, use the formula pressure of a liquid is equals to density, gravity and depth. Here depth, the level is 15 centimeters, so it should be in meter. So you should convert into meter. So what's the answer for this part? 1.2 exponent 5 minus 1 exponent 5. So it will be 0.2 into 10 to the power 5. And density we don't know, gravity is 10, and the depth, that was 15 centimeters, so we have to convert into meter, 0.15. Is it clear? The depth is given in centimeter, but it should be in meters. So which is 0.15. And you'll get the final answer for the density of the liquid. Next question. Water has a specific heat capacity of 4200 joule per kilogram degree centigrade and a boiling point of 100. What is meant by the boiling point? The term boiling point means temperature at which liquid turn into gas, and a complete definition when temperature at which liquid pressure is equals to atmospheric pressure, or gas pressure is equals to atmospheric pressure, or vapor pressure equal to atmospheric pressure. The next part, the mass of 0.3 kilogram water at its boiling point is poured into a copper container, which is initially, so that's initial temperature. After a few seconds, the temperature of water in the container is 95. Calculate the energy transfer from the water. So we have the mass, we have initial temperature, final temperature. We need how much energy transfer. So whenever there is a change in temperature, we use the formula for specific heat capacity. E is equals to Cm delta T. So 0.3, that is the mass, specific heat is 4200, and the temperature change as it cooled down, because they mention a mass of 0.3 kilogram of water at its boiling point. So water was at boiling point, and it was there in a copper container which was initially at 11. So temperature of the container was 11, but the temperature of the water is 100, because the water is losing energy and the copper container is gaining energy. That's why it was 100 minus 95. not in 95 minus 11. The next part, calculate the thermal capacity. Thermal capacity means energy required to change the temperature of a given mass by 1 degree. So what is the change in temperature for copper? And our assumption is that all of the heat energy from water is transferred to the copper container. So C is equals to E divided by delta T. E is the energy which is the same as what is transferred by the water to container, and divided by temperature change 95 minus 11, which will come out 75 joules per degree centigrade. So that is like effort to change 1 degree temperature change for this container, we need 75 joules of heat energy. Water from the container evaporates and the temperature of the remaining water decreases slowly. Explain in terms of molecule why evaporation causes the temperature of a remaining water to decrease. And it's of 3 marks. So basically what happened, the most energetic molecules gain energy from the surrounding water molecules or neighbors or surrounding and break the intermolecular force and escape. So the molecules which have left behind or molecules which are left behind will have low energy. That is the reason why evaporation is also known as the cooling process. The cooling process because the particles at the surface, they gain energy. The most energetic molecules gain energy from the surrounding, break the intermolecular forces and escape. So the particles or the molecules which are left behind will have low energy. That's why the evaporation is known as the cooling process. And it's of 3 marks, so 1 point you have to include is about the forces. The most energetic molecule escape and the energy of the ones that remain decreases. The energy used to break the intermolecular forces. So these are some sample answers. Moving on to the next question. The distance between the center of a thin converging lens and the principal focus. What is meant by the term principal focus of a thin converging lens? So it's a point where all the parallel light rays converge on principal axis. That is called principal focus. The next part, the lens is used as a magnifying glass to produce an image, eye on the object. Underline the term that describes the nature of image produced as a magnifying glass. So the magnifying glass, it will be enlarged. It cannot be seen on a screen, so it's virtual and it is upright. Figure 5.1